Hello, everyone, and welcome to the session. This is Ensemble Techniques session. And as part of this Ensemble Techniques, we are going to talk about, to get started, decision tree. And then we will try to understand on what are the disadvantages, what are the cons. Once we are done with that, we will try to understand how bagging techniques are going to help us overcome this issue. Once we are done with this, we will then get to a different variant, which is called as random forest. I would say a different variant of decision tree rather. Once this is done, we will get into boosting. Within boosting, there are three algorithms that we are going to talk about. One is AdaBoost. And then we'll talk about gradient boosting algorithm. And then we'll talk about extreme gradient boosting algorithm, right? These are the algorithms that we will talk about. Post that, we will get into stacking. And of course, we'll talk about voting as well. Alongside that, of course, when it comes to voting, we will talk about hard voting, soft voting. And then we should also talk about a few other terminologies. Let me put it as terminologies. But the first algorithm that we are going to talk about would be decision tree, because the knowledge of this is important, pivotal, for us to understand the knowledge of the other algorithms. Okay. So we'll get started. And the first thing that we are going to talk about for today would be decision tree. I'm sure a few of you all would have already undergone decision tree algorithm. It would be a kind of recap for you all, but you'll have to bear with me because I need to certainly talk about this before we proceed further. Yeah, there is a question, I believe. Yeah, Roshan.
Yeah, Bharani, so this bagging technique after decision tree that you have mentioned here, is this not part of the text mining? So how is it fitting in here?
In text mining, what bagging is there? Sorry?
Bag of words.
Bag of words is bagging.
Okay, that's different from bag.
Absolutely different. Bag of words is different. Bagging is different.
Right? Understood. Yeah. Okay. I got a little. Yeah. Understood.
Okay. I'm sure my voice is audible. That's the reason why people are able to ask questions as well. So Shrikant, you'll have to check the settings at your end. Okay, before we get started, let me get to the mind map. We have this project management methodology called as CRISP MLQ. And within that, we have a lot of phases. We have phase 1, which is business and data understanding. And then we have phase 2, phase 3, phase 4, phase 5, and phase 6. Yeah, these are the 6 phases that we have. And as I've told you guys, we will be adding more and more information as we proceed further to this mind map. So I request you all to read the mind map on a daily basis, right? At least one time you have to read. And here we have the success stories also listed. Business success criteria, machine learning, economic success criteria, which are also pivotal. And then we have data understanding. Within data understanding, we added new things, new metrics. We have pre-training bias metrics, post-training bias metrics, so on and so forth. So we will be adding more and more information, which will help you differentiate yourself from the other people when it comes to interviews. Then you obviously clean the data, prepare the data, etc., and then you get into machine learning. Within machine learning, we have something called as supervised learning. Supervised learning is also called as predictive modeling. We are in predictive modeling now, and we are going to talk about ensemble methods. And this session is called as masterclass session, wherein we are going to, cover a specific topic end to end, decision tree, and followed by the other algorithms. Yeah. And any reason you asked that question? Sorry, up to 3 in the sense this. Okay. Within that, did we cover everything? We didn't cover, right? That is why I'm covering the topics which we haven't covered. How does it matter, right? So the topics which I haven't discussed, we'll be discussing today. Okay. Yeah. So to proceed further with this, obviously you need to have knowledge about machine learning primer, which we have discussed, right? Here, please remember one thing, that you either split your data into training and test, or you split your data into training, validation, and test. Okay, it's up to you on how you split the data. When do we split the data only into training and test? When we have less hyperparameters. If you have less hyperparameters, then will we perform less experiments or more experiments? What is a hyperparameter in the first place? Hyperparameter is an option within a machine learning algorithm which can be changed for experimenting. Hyperparameters are options within algorithms which can be changed for experiments. If you have less options, then will there be less experiments or more experiments? Less experiments. Because I have less options, I'll be doing less experiments. Wake up, wake up. Is this your first class? First class? Okay. So I request you to keep answering, because I also need to understand. People who are joining online, please keep answering, friends. Okay. So if you have less hyperparameters, the number of experiments performed will be less. Hence, you need not have another split in your data called as validation. If you take your data set and split it into training and test, job done. But if you have more hyperparameters, you need to perform more experiments. If you have more hyperparameters, you need to perform more experiments, and hence you're going to have training data, validation data, and test data. The essence of validation data set is to help you all perform more experiments, because when you train the data, you can train your data with various hyperparameters. You can keep changing your hyperparameters, keep training your model, but then you end up validating on the validation data set. Or in simple sense, you test on the validation data set. Once you figure out that these are the perfect set of hyperparameters, which is giving me the best accuracy possible, then you take that model and test it on the test data. Okay. All right. Once you're done with building the model, you are always expected to compare the training error and test error, or training accuracy and test accuracy. Errors should be less, or errors should be low, whereas accuracy should be high. This is the ultimate objective, right? Either take accuracy or error, doesn't matter. If you're comparing the error values, both your training error and test error should be low and close to each other. Then you call it as right fit model. Okay. If your training error is low, that means you built a very good model using your training data. But the moment you test it on the test data, if the test error is high, that scenario is called as overfitting or variance. Okay. And we fix this issue pertaining to variance or overfitting by using regularization techniques. Okay, by using regularization techniques. Okay, our friend is talking about data while I'm talking about accuracy and error. So I will try to understand our friend's understanding. Yeah, Marvin. Marvin, can you please unmute yourself? Yeah.
Yeah, hello. Yes.
Yeah, I'm talking about error here. I'm hoping that you're also talking about error, but you're misquoted error as data is what I feel.
No,
Otherwise, yeah, you can ask me. Yeah.
I was talking about this training, validation, and testing.
Yeah. What are you talking about training, validation, and testing?
Like,
Please?
how do we decide that which is which is less data and which is more data? Like, is there some value that I have to decide?
Which
like,
is less
if I
data
have to,
means? Okay.
like, if I have to,
Initially,
yeah.
Before you get started on any project, you understand the business problem, and to solve the business problem, you collect the data. Okay. Say I collected the data. Are you talking about the amount of data which is collected? How do I decide whether it is less or more? Is that your question? Yeah, Marwan.
Yes, yes. Yeah, like, how do I decide I have to
So you're not
consider only
talking
training
about
and
machine
testing?
learning. Your question is, if I go collect the data, is it less or more? How do I decide? Is that your question? I repeat.
Yes, and how do I divide like training,
No. First,
validation,
we'll
testing?
take it step by step, Marvin. I don't have multi-processing capability, unfortunately. We'll take one at a time. Okay? What is your first question? You understood the business problem and then you collected the data.
Yes.
If say you have 10,000 data points, is this data set small or large? Or is this data sufficient to train my model or not? Is that your question? First question.
Yes, yes.
My dear friend, according to statistics, and this is for everyone, in the good old days, my friend, good old days in a sense, probably some 20 years ago, when we did not have sufficient storage to store the data, the max that we used to have is what, 40 GB, 50 GB, so on and so forth. In those days, when the compute also was less, meaning we used to have probably 256 MB RAM, 512 MB RAM, right? In those days, since the processing was not sufficient, storage and compute were not sufficient, people were sticking to the thumb rule that if you have minimum 30 data points, minimum 30 data points, it is sufficient for you to get started with your statistical analysis. However, as and how technology started growing, as and how the compute started becoming faster and faster, as and how you have P3, P4, P5, P7, right, P9, so on and so forth, whatever, right, I3, I5, I7, and as and how the storage started increasing, people were saying that the more the data, better it is. Better the analysis. To answer your question on how much data is sufficient, it really depends whether you're working in the space of ISRO, NASA, nuclear power plant kind of projects, or you're working on projects pertaining to e-commerce or some kind of banking, etc. If you look at e-commerce, there'll be huge amount of data because every second customers will be purchasing left, right, and center. Every second you'll have huge number of transactions happening. With respect to banking also, there'll be huge number of credit card transactions or other banking transactions which happen. In this kind of scenario, the amount of data that would be available for you would obviously be large. In this kind of scenarios, the amount of data that would be available to you would be obviously less. Given this context, how much data is good enough is something that we cannot understand upfront. Okay, the more the data, better it is for you. Making sense, Marvin? So there is no question on how much data is good enough, how much data is sufficient. If the customer has more data, your model will be better. If a customer gives you less data, your model will be substandard.
Okay.
Okay. Yeah, that was your first one. Yes. Next question. Next question, Marvin.
Yeah. Next question was like, if I have to divide for training, validation, and testing.
Yes.
So on what basis I have to decide, like, what is considered as a less parameter and what is considered as like
okay.
maximum? Yeah.
Are you done with K&N algorithm, Marvin?
Yes. Yes.
What is a hyperparameter here?
Those are what I understood is they are data points.
What is in K&N algorithm? You know, right?
K
My
nearest
question
neighbor.
is very simple. What is hyperparameter when it comes to K&N algorithm? K value.
K value, yes.
Okay. So this is the only hyperparameter in this algorithm.
Okay.
Whereas when it comes to decision tree kind of algorithm, you'll have many things like maximum depth, minimum sample split, minimum leaf nodes, minimum impurity, so on and so forth. Now you tell me, Marvin, that if I give you data and if I ask you to build K&N algorithm, are you going to split the data as training, validation, and test? Or would you split that into training and test?
Training and test.
Why? Why would you do that?
Because there are lesser hyperparameters.
You have the answer, Marvin. You have the answer. Okay, because every algorithm, one algorithm might have 6, another algorithm might have 20, another algorithm might have only 3, right? So the question that you've asked is very subjective in nature. Okay, absolutely, this is very common sense driven. If you have a single hyperparameter, then you have less hyperparameters. If you have less hyperparameters, then you split the data into training and test. But if you have more number of hyperparameters, then you split the data as training, validation, and test. Simple. Okay, but since there is no thumb rule as such, there is no statistical rule, forget about it. There is no thumb rule also to decide on which algorithm has less and which algorithm has more. However, if you are in doubt, if you are in, some kind of a dicey type thought process, then I would say try out both. Split the data into training and test, split the data into training, validation, and test. Yeah, it's up to you. Okay. Yep, Satish, I knew that, but I wanted him to, explain me clearly because Marvin was talking about data. So that's why my first question was it related to data or something else? Marvin, is it clear? Can I move on? Okay. All right. So if your model is overfitting, or overfitting is also called as variance, we proceed further with regularization technique. Having said that, if your training error itself is high, what does that mean? You did not even train your model well. Then will it work well on the test data? No. This scenario is called as underfitting or bias. To fix this issue, once again, you can either resort to regularization techniques, or you can fix this problem by transforming the data or by performing better feature engineering or by getting more observations or more features. So the moment you try to use regularization techniques, okay, you are going to do a trade-off between bias and variance. And you'll ensure that you end up building a right fit model. You end up building a right fit model. Okay. All right. So now let's get into decision tree algorithm. So we have decision tree algorithm, which is called as a rule-based technique, which is also called as non-parametric method or hierarchical model. These are the different names given to decision tree. But just remember that it's rule-based and it is non-parametric. And when we talk about, say, for instance, an algorithm such as linear regression or logistic regression or any of the regression techniques, if you talk about any of the regression techniques, or if you talk about any of the neural network algorithms, in these algorithms, you will have equations like this. I request everyone to please maintain a running notes, friends. Whatever I'm talking, just keep a note of it, keep writing it while the class is being discussed, because that will help you stay focused. Otherwise, there is no use in attending the training itself. Okay, I'm upfront telling you. If you don't write it, then forget about it. Then, when it comes to neural network algorithms, you have W1 x1 plus W2 x2, so on and so forth. And these beta values or this B values are called as parameters. All of these are called as what? Parameters. All of these are also called as parameters. These are not hyperparameters. These are called as parameters. All of these, including beta naught, including B, everything is called as a parameter. These are the parameters which are learned by your model. If you use regression analysis, your model will learn these beta values. If you run neural networks will learn these weights, which are called as parameters. So these algorithms are called as what techniques? Parametric methods. Whereas in decision tree, you will see nothing of this kind. It will not learn any parameters, but it's going to learn what? Rules. Okay, it will learn rules. Okay. So decision trees, as the name itself says, it will have a tree kind of a structure, and you'll have something called as a root node, branch node, and leaf node. These are the three nodes that you would see. Root, branch, leaf, like a typical tree that you have. And decision tree is based on divide and conquer, like what Britishers have done, right? Divide and conquer. So you'll have a specific variable or a feature, a root node. And then you keep splitting it. Keep splitting the tree further. Keep splitting it further. Keep splitting it further in that way. And the first node is called as root node. These nodes, which you see here, are called as internal nodes or intermediate nodes. And then you have final set of nodes, which are called as leaf nodes or terminal nodes. Okay, now we are going to talk about a specific algorithm called as greedy algorithm, okay, which will also have certain stopping partitioning conditions. I told the decision tree you keep splitting it, but to what extent will you split? When will you stop? Right? Is something that we need to understand. A few 101 about decision tree or any tree-based algorithms is that tree is constructed in a top-down recursive partitioning divide and conquer manner. Continuously, recursively, continuously, if you keep partitioning your data. At the start, you get started with the root node. Okay? And decision tree or any tree-based algorithm does not like continuous data. They don't like numeric data. So if you have numeric data, you need to discretize. Discretization has to happen. If you do not do that, your algorithm will automatically, come up with some partitioning. That will only discretize your data automatically. Okay? If you feel that, no, I don't want any automatic discretization, I want this discretization to happen based on some logic, your thought process, then you do it. For example, if you have income, if you leave it to decision tree, probably it will say high income, low income, two categories. But maybe you might feel that, no, I have high, middle, and low income group. If you want it in that manner, you only have to manually do it. Because if you leave it to algorithm, it will decide based on some rationale. Okay. So everything which is listed down here, we'll try to understand using some example. So this is the data set, wherein you have 14 observations, 1, 2, 3, 4. In that way, we have 14 observations, and you have various features or inputs. X1, X2, X3, X4, right? There are 4 features, and you have a label, an output variable, which is, will a person buy a computer or not? And you have 14 observations here. Age, income, is a specific person student or not? Is a credit rating fair, excellent or not? And would a person buy a computer or not? Okay, this is the data that we have. Now assume that in this, I'm choosing student as the root node. Student has what? Yes and no. It has no, and it also has yes. Wherever you have no, take all the corresponding values pertaining to that. Wherever you have no, take the values corresponding to that. Here also you have no, so take the values corresponding to that. Here also you have no. Here also you know. Take all these values and put it in a table here. So here you have no, and all the values are listed down here. Then we also have student as yes, and you have all the values pertaining to that. Okay, again, you are going to split this and you're going to split this further. And this time we are choosing income. If you look at income, income has high and medium, only 2 levels. Whereas here, income has low, medium, and high. 3 levels. Low, medium, high, and medium. Okay, and then you split it. Until when should I continue splitting? You continue splitting until you have a single record in that tree, or until both the classes have the same value. Okay, you continue splitting until there is a single record, or both the records have same value. So your splitting of the tree stops in these cases. It will not grow any further. But here, do you think the split happens further? Yes, because if you look at the output variable here, you have no and yes. So you have to further split this. Here also you have yes and a no, so you need to further split this. Here also you have yes and a no, so you need to further split this. But these two, we did not split because here you have a single record, here both the records are the same. Now we'll continue splitting further. Do you think we need to split this further, this branch? No, because both the classes are the same, you don't split it further, you stop. Okay. Here, there is no scope of splitting because you have a single record, single row. Here, do we split it further? Yes. Why? Because you have yes and a no. Here, do we split it further? Yes, because both are different. Here, do you split it further? No. Why don't you split it? Because both the classes have the same value. Here, do we split it further? Yes. Why? Because both are different. Okay. So continue splitting in that way. And what does the decision tree do? It will give you rules. Decision rules. For example, if the person who entered your shopping, your shop, if that person is not a student, if the income is high, if the age is less than or equal to 30, would that person buy a computer? No. If the person who entered your store is not a student, income is high, age is 31 to 40, would that person buy a computer? Yes. So every branch, this is tree. Trees have what? Branches. So every branch would be called as one rule. Every branch is called as one rule. Okay. So look at this. Yes, the person entered is a student, income is low, credit rating is excellent, age is 31 to 40. Then would the person buy a computer? Yes. In this way, your decision tree is learning what? It is learning rules. These are the bunch of classification rules. Not a student and income is high and age is less than or equal to 30, person will buy a computer. Not a student and income is high and age is in between 31 to 40, person will buy a computer. Yes. Here, no, here, yes. Okay, so in this way, classification rules are formed. From there on, whenever you have new data, new information, okay, it will just look at one of these classification rules and it's going to map it and give you the output. Okay, if I have more data, I'll have more rules. Okay, so the model will be better in terms of accuracy. Right? If you have more data, obviously your analysis will be much better. Okay. Yeah. So what I would recommend you guys is wait until I complete the decision tree algorithm completely. Then I'm sure 99% of your questions will be answered. If there are any questions which go unanswered despite all this, then you ask your question to be better. So, yep. So Venkatesh, hope you got me, right? Now, instead of student, But then, yeah, those are the, I mean, for your question, I'm going to answer. But it's included in the training itself. So we'll complete this and then we'll take the questions. Suppose in this data set, instead of choosing student as a root node, what if I use income as a root node? What will happen? If you choose income as a root node, then income is low, high, and medium. So you get different splits. Again, on age, etc., you're splitting further, continuing that split. And after you complete the complete tree, if you grow the tree completely by splitting, then you'll have different set of classification rules. Now, the million-dollar question is, should I use student as a root node, or should I use income as a root node, or should I use some other variable as a root node? Okay. To this, answer is that variable which has the highest information, if this is the data set. These are your features or inputs. Inputs or features. And this is your output variable. Which feature or which input should I choose as a root node depends on which of these have high information. Now, what is this information and how do I decide on which variable has the highest information, right? That's what we need to answer. We'll answer that using something called as entropy and information gain. We are going to understand this. And these are the very simple formulae that we are going to apply. How many of you feel that it's, appearing to be very simple? No, not simple. Yeah, very simple 3 formulae. The moment you look at it, I'm sure you'll understand. No? Okay, I'm sure you'll not understand, right? So we'll make it very simple. We'll use a very simple example. To understand this, I am going to talk about okay, I'll talk about information, or I'll say information theory. Okay. If I say, here's one of my favorite examples. Sun rises in east. Would you say, amazing, what an information this guy has given today? I never knew. Would you say that? What will be the information contained in this? Very low. Because you anyways know that sun rises in the east. If I also say sun rises in the east, you'll be like, come on. Right? There's no information in that. Why? Because the probability would be very high. %, sun rises in the east only, until unless you change the directions for your own self, right? Until unless you say that this is not east, this is east. Until unless you change on your own, sun rises in the east. It's a universal statement. So probability is very high. If probability is very high, information will be low, obviously. If I make another statement that there was earthquake, but there was tsunami in Chennai, would this be a news for you? Okay, suddenly you'll say, oh, is it? So it won't happen frequently, right? What is the probability that there'll be tsunami in Chennai? Very low. Whenever probability is low, information will be high. When this flashes on the news channel, you'll be like, oh my God, what happened, right? So you'll start paying attention because the information contained in it is very high. So can I say information contained in any event is inversely proportional to the probability of that event? If the probability is high, information is low. If the probability is low, information is high. That means information and probability values are inversely proportional to one another. And we usually take the log when you feel that calculations will become simpler. Log is only used to have some mathematical simplicity in calculations. Take a very big number, take a log of that. What do you think log of 10,000 would be? If you take log of 10,000, say 10,000, obviously that's a very big number. Or say 100,000. If I take a log of that, the value will become very small. So my math calculation will become faster. That's the only reason why people use log. Okay. Anyways, that aside. Now, if you want to take this probability to the numerator, what would happen? It would become minus log of probability of event. Okay. This is the formula that you get. Just I'm taking it to the numerator, that's it. Are you all here? All good until now? Okay. Now, okay. Anyways, so I'll just erase this. And this is a formula that we have. Information is proportional to minus log of probability of event. This is a formula that we deduced from that simple example that sunrise in the east, tsunami in Chennai, etc. Now, we discussed about mean and we discussed about expected value. Remember, in the initial days, we discussed about the difference between mean and expected value. Expected value is also called as mean. Suppose you invest your money in some government bond. Government would certainly say that, I'll pay you 8% return or 12%, whatever they promise, they'll pay you. So if the values are certain, certainly if you're going to get 8% return on investment on an average, then this is a formula that would be used to calculate. In 1 year, you will get 8%. In next year, you'll get 9%. Next year, you'll get 7%. On an average, government will say, I'll pay you 8%. In the next 5 years, on an average, I'll pay you 8%. Government will stick to that. Whenever you invest in stock market, say you invest in TCS stock, do you think they will tell you certainly that, after 5 years, on an average, you get 10%? Can they say that? It fluctuates very, rapidly. The variance will be very high. Hence, you are really not sure on what will be the return on investment if you invest in other stocks, apart from government bonds. So there, since probability is involved, the expected value was written as xi into probability of xi. If you remember, this was something that we spoke about in the initial days of the tree. This is how you calculate mean. The moment you have uncertainty, what will you have? Probability values. This is also like that. This is the information, and information is proportional to minus log of probability of event. What is this? Information gain. Or I'll just put this as information. Now, if you want expected information, similar to this. Now we calculated mean. Now to move from mean to expected mean, you're just taking that value and multiplying it with probability. Right? That is what we are doing. We're taking this value and multiplying it with probability. Here also you do the same thing. So expected information is equal to, take this value, okay, this minus sign, I'm putting it here. Okay, take this value and multiply it with probability. So I can also say probability of the event into log of probability of that event. X into probability of X. In that way, probability into X. Clear? So that is how this is reduced. And this is given a name called as entropy, which is also called as measure of impurity, loss, error, if you want to call it that way. But error and loss are different, but still, if you want to call it as error for now, it's absolutely fine. So this is a formula for entropy. Clear? All right. Back to our discussion. Now, let's take a specific example here of a data set wherein I need to get rid of this. Wherein you have all these x1, x2, x3. Say you have 3 inputs or 3 features, and then you have an output variable which says useful for play. A specific ball, cricket ball or football or whatever, the size of the ball, color of the ball, price of the ball, these are the 3 inputs which are given. Given these 3 inputs, we need to check whether it is useful for play or not. Okay. And what we will now do is we will try to find out how much information is available in this input, how much information is available in this input, how much information is available in this input. How much information is contained in each of these features is what we want to find out. Why do I want to find out that? We want to find out that because we want to decide which feature I need to use as a root node, because I need to split my tree. I want to split my tree in this way, but what should be the root node? How do I decide? Based on information gain. That variable which contains highest information would be chosen as your root node, right? Now, a better way to understand that is not to get into these formulae. Now I'm sure you will be able to tell me, hey, what is this formula? Expected information or entropy. We just calculated it, probability into log of probability. Now these two also we are going to understand. But if you look at these formula, you'll be like, oh my God. Right? So don't worry, I'm going to help you understand this. Okay. Let us choose ball size. But before that, let me write the formula also here. Formula is information gain of any variable or feature is equal to entropy before minus entropy after. The good part is we know the formula for entropy. Minus summation of probability into log of probability. Okay. Now, let's take ball size. But even before I take ball size, we need to figure out what is entropy before. Okay. That means before you split this tree. How many classes do we have here? 2 classes. Yes or a no. So it's called as a 2-class classification problem. This problem would be called as what? 2-class classification problem. Why? Because it has 2 classes, yes and no. Since you have 2 classes, I can write this formula as minus summation of I equal to 1 until 2 probability of xi into log of probability of xi. Usually we give base 2, base 2, base 10, natural log, base e. You can export that. It's all very trivial stuff. Okay, this is written as minus probability of x1 into log of probability of x1 base 2 minus, when you substitute I equal to 2, you get probability of x2 into log of probability of x2 base 2. Okay, that's all. I just expanded the formula. I just substituted I equal to 1. I've written it down. Minus, I substituted I equal to 2 and then I've written this down. Now, what is probability of x1 and probability of x2? This is what we want from this data. You have 2 classes, yes and a no. Probability of x1 is yes class. So what is probability of x1? Equal to yes class. Okay. How many yes do we have? 1, 2, 3. 3 out of 5. So this will be 3 by 5. And what would be probability of x2? It would be nothing but no. How many no do we have? 2 out of 5. So this will be written as 2 by 5. Now you write down minus 3 by 5 into log of 3 by 5 base 2 minus 2 by 5 into log of 2 by 5 base 2. You have to be very fast at doing such calculations. Do you know what you'll get if you calculate this? 0.97095. Can you calculate that fast? No? To calculate, you just need to pre-calculate and keep it. Okay. All right. So we have entropy before. Wonderful. Now what do we want? We want entropy after. So what I'll do is, I'll just erase only those things which we are not going to repeat. All right. Now entropy after. If we take, for example, ball size as a variable. For all the variables we need to calculate. Now let's just take ball size. If I take ball size, then what decision tree does is, okay, it is going to first split the tree using 1. It will take the minimum value, 1. It will say, okay, if the ball size value is less than or equal to 1 and greater than 1, it will use this as one condition. It will calculate the entropy. What is entropy? Measure of purity or measure of impurity? Impurity means what? Error. Right? So it will calculate that entropy for this rule. And then it will go with the second rule, 10. Less than or equal to 10, greater than 10. Again, it will continue the algorithm and it will calculate the entropy after. How is it calculated? We'll get there. Then what will it do? It will choose 50. Less than or equal to greater than. It will again calculate entropy. Then it will take 100. Less than or equal to 100, greater than 100. And then it will calculate what? Entropy. Then it will take 1000, because that's the next value. Greater than or equal to 1000, sorry, less than or equal to 1000, greater than 1000. Again, it will calculate entropy. Out of all these entropies, because you have 5 unique values, it will take all of those 5 unique values as conditions to split. And for each and every value, it is going to calculate entropy. And then which condition will it choose out of all those entropies? Entropy is measure of impurity. So less the better or more the better? You want less impurity or more impurity? Less impurity, right? Impurity error should be less. So for every condition, it will calculate entropy, and then it's going to choose that condition where you get the least entropy, which is nothing but error only. For now, just assume that it is error. Out of all those 5, since I have already understood or pre-calculated in my mind, I'm going to choose one condition which gives the best result. I will say less than or equal to 50, greater than 50. Okay. Yeah. Yeah. Right. Right. Absolutely. You're right. Only for example, I'm showing this. But what if this is count data? This is not continuous data, but this is count data. Right? Price is continuous, no doubt about that. Ball color is categorical, but this is count, right? Ball size. Maybe it is count. Assume that it is count. If it is count data, then you need not discretize it. You would not. You will tell to decision tree that this is object. Remember in Python, when you load this, what will Python start treating this as? Integer. But you will tell to algorithm that, do you know what? This is not an integer, this is an object. When you tell to your algorithm that this is object, it will not do any discretization. But yes, you have a point. If you discretize, obviously you'll have less levels. No, there is no such thing. Depends. Okay. So if you have a ball size less than or equal to 50 and greater than 50. And now it will go to the first entry. Say you're applying this rule. You're applying this rule, prediction rule or classification rule on this. You're going to the first rule. 10. Is 10 greater than 50? No. Is it less than 50? Yes. So what would be the predicted value? Predicted value will say, this is rule for yes, this is rule for no. Predicted value will say, if the ball size is less than 50, predicted value will be yes. But in that, what does the actual value say? Actual value also says yes. So is there any error? No. Okay, let's go to the second. 1. Is 1 greater than 50? No. Is it less than or equal to 50? Yes, it is less than 50. Less than or equal to 50 means predicted value will be yes. And what does the actual value here say? Yes. Now, we'll go to the third rule. We have a value called 50. Is 50 greater than 50? No. Is it less than or equal to 50? Yes. So the predicted value says yes. The actual value also says yes. Okay. The right side is done. Now let's go to the next value, which is 100. Is 100 less than or equal to 50? No. Is it greater than 50? Yeah. 100 is greater than 50. So what does the predicted value say? No. No. Predicted value here says no. And your actual value also says no. So again, there is a match. Again, I'll go to this value, fifth row, 1000. Is 1000 less than or equal to 50? No. Is it greater than 50? Yes. So the predicted value will say no. And the actual value also says no. Is there any mismatch? No. Now let's calculate entropy. But here you have two sides, entropy to the left side and entropy to the right side. Okay. Because there are two splits. So let's calculate the entropy for both these. Let's first get to the left side. In left side, it is less than or equal to 50. Less than or equal to 50 means these three. Right? These three. Less than or equal to 50. Here, how many yes do we have? 3. 3 out of 3. 3 by 3 is nothing but 1. And how many no do we have here? 0 no. Out of 3. So it is 0. Now, if I were to calculate entropy for this left side, what would the formula be? Minus this P of x1 is 1. So 1 into log of 1 base 2 minus probability of x2 is 0. So it becomes 0 into log of 0 base 2. 0 into anything will become 0. Log of 1 is 0. So minus 1 into 0 would be 0. So ultimately, entropy towards the left side would be 0. Any doubts? Which one? This one? So we are calculating for left side first. Left side, what is the condition? Less than or equal to 50. Is 10 less than 50? 1 less than 50? 50 less than or equal to 50? Yes. So I'm taking only these three. Correct. For this side. Now I want to calculate probability of x1. x1 is nothing but yes. x2 is no. How many yes do I have here? In how many places? 3. 3 out of 3 is 1. How many no do we have here? 0 out of 3, which is 0. So I got P of x1 and P of x2. I'm just substituting here. Wherever I have P of x1, I'll put 1 into log of P of x1 is 1. Wherever I have P of x2, I'll take the P of x2 value, which is 0. So 0 into log of 0. 0 into anything is 0. Log of 1 is 0. So minus 1 into 0 will also be 0. 0 minus 0 is 0. So I'm saying ultimately left side of the entropy will be 0. Clear? Okay. Now, okay. Now what we will do is we will calculate the entropy towards the right side. What is the right side? This happens to be the right side. Left, right. Okay. Here you have greater than 50. Okay. So you need to choose only those where you have greater than 50. Greater is 100 greater than 50? Yes. 1000 also greater than 50. So only these two entries you select. Okay. Now, only 2 we have. How many yes do we have here? 0. So 0 out of 2, which will be nothing but 0. And how many no do we have? 2 out of 2 will be 1. So substitute P of x1 is 0. So minus 0 into log of P of x1 is 0. So log of 0 is 2 minus. What is P of x2? 1. 1 into log of 1 base 2. 0 into anything is 0. Minus 1 into log 1 is 0. 1 minus 1 into 0 will be 0. 0 minus 0 will be 0. So we are also getting entropy towards the right side as 0. entropy towards the right side is also 0, left side is also 0. So done, I calculated entropy for both left and right side. Now we need to combine that. When you want to combine these two to get entropy after, let me erase these things. Right. Entropy after would be entropy towards the left plus entropy towards the right. You need to add these two to be able to arrive at entropy after. You need to add these two to get entropy after. On the left side, we had these three. 3 out of 5 entries were on left side. And on right side, we had 2 entries, 2 out of 5. So 3 by 5 into, what was the entropy on the left side? 0. Plus 2 out of 5 were on the right side. So 2 by 5 into entropy of right is also 0. So when you add these two, you get 0. Okay. So entropy before, I got minus so much. Entropy after becomes 0. 0.97095 minus entropy after is 0. That would be nothing but same value, 0.97095. You get the same value, right? This is what? Information gain. Information gain is entropy before minus entropy after. We calculated entropy before, we subtracted it from entropy after, and then you get a value, which is nothing but information gain. Okay. What does this mean? This means that by splitting the decision tree with ball size as a feature, we were able to reduce the uncertainty in the subtree. Subtree means small tree within the overall tree. To take the small tree, that's a subtree. So we were able to reduce the uncertainty in the subtree outcome by 0.97. That's the interpretation, English interpretation. Now look at this and tell me, okay, or this is what I would say. Take quick 5 minutes, or so, let me put it as 10 minutes, and calculate the information gain for price. Okay, please calculate information gain for price. This is nothing but entropy before minus entropy after. And since you're doing it for price, it's a 2-class classification problem. You either have to classify something as yes or no. Yes or no. And here you need to come up with a rule. What is the rule that you might want to come up with? Probably your decision tree will calculate for all the values. It will say less than or equal to 1, greater than 1, less than or equal to 5, greater than 5. What is the other unique value? 10, less than or equal to 10, greater than 10. You will calculate for everything. But let me tell you that for less than or equal to 5 and greater than 5, you get the best result. So use that as a rule. And yes, calculate the entropy towards the left side and calculate the entropy towards the right side. Using the same logic, same rationale. Formula also is given here. You just need to calculate for everything. Probability of x1, which is nothing but yes, and probability of x2, which is nothing but no. Solve it, take a quick 10 minutes time, and then we'll get back. I'll pause the recording until then, or I'd rather stop this.